Okay, welcome back. Today we're going to introduce the notion of a series. So suppose you took E and you wrote it down as a decimal, 2.71828, blah, 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 blah. Goes on forever. What do you mean by that? Well, you mean 2 plus 7/10 plus 1/100th plus 1,000th plus 2 over 10 to the 4th plus 8 over 10 to the 5th, etc. So that's what you mean. Well, what does that really mean? How do you add up infinitely many numbers? Let's go to a much simpler example. What if you wanted to add up these numbers? And ... means you follow this pattern forever. Just powers of 2 in the denominator. So you'd start adding. So the first term is a half. Then you get that much, 3/4. Then you get that much, 7/8. Then you get that much, 15/16, and so on. So as you keep adding, you generate this sequence of numbers, which certainly looks like it's approaching 1 in the limit. So that's the idea. So if you start with a sequence of AN, then we're attempting to add them using the sigma notation. We're attempting to add them all. So you're looking for something like that. So we do exactly what we did here. We form what's called the sequence of partial sums. S1 is the first, S2 is the sum of the first 2, S3 is the sum of the first 3, and so on. Sn will be the sum of the first n. So I'm going to switch the subscript to I so I can sum from I from 1 to n. So you get the sequence S1, S2, S3, S4, S5, etc. That's the sequence of partial sums. Question, does it have a limit? Maybe it does, maybe it doesn't. So we define, in this situation, if this sequence of partial sums has a limit, then we say the infinite series converges to whatever that limit is. Right? By definition, the sum of this series is the limit of the sequence of partial sums. Call it S. If the sequence of partial sums does not have a limit, then we say that the series diverges. Right? So it either converges or it diverges. Some converge, some diverge. And so we want to meet some examples. Probably the most elementary example, and comes up all the time, is it's called a geometric series. That looks like this. Start with, pick a number A and a number R. R is called the ratio. And here's the sum. A plus AR plus AR squared plus AR cubed plus ... Turns out we can handle this pretty easily. Why? Because it's easy to find a nice simple expression for the partial sums. Usually it's not easy, but in this case it's easy. So let's do it. First think about the case if r equals 1. If r equals 1, then all these terms are just a. You're adding up a over and over, so the nth partial sum is a times n, which of course goes to infinity. I'm assuming, of course, that a is not 0, otherwise there's nothing to talk about here. So this would diverge. So what if it's not 1? Then what? Then let's write out, here's the expression for Sn. All right, so it starts sort of with AR to the 0, AR to the 1, AR to the 2. I'll go up to AR to the n minus 1. Here's the little trick, multiply by r. That has the effect of taking all these terms and shifting them down 1. When you multiply by r, this becomes that, this becomes that, this becomes that, and so on. And finally, this one becomes that one. So these sums almost completely overlap, right? All of these terms from here to here overlap. So I subtract this minus this. All these cancel. I'm just left with a minus ar to the n. Factor out Sn and solve. And there you go. We get this nice, simple expression for the nth partial sum. This we can handle. This is easy to tell limits. See, if r is in this range, so this is basically the absolute value of r less than 1, then you take higher and higher powers, they go to 0. It's like a half squared, a half cubed, that sort of thing. They go to 0 if the absolute value is less than 1. So that means this guy goes to 0, so this thing in the limit becomes a over 1 minus r. And there's the answer. We get a limit, so it converges, and in fact it converges to this. If r is bigger than 1, or less than or equal to negative 1, then it diverges. That's like taking higher and higher powers of numbers bigger than 1. Of course, they're going to infinity. So you get divergence. So, in conclusion, we get the full story for geometric series. They converge if r is strictly between minus 1 and 1, and it converges to this. It's the first term divided by 1 minus the ratio. Otherwise, it diverges. By the way, this is called the ratio because r is the ratio because it's the limit of successive terms. This divided by that is r. This divided by that is r. This divided by that is r. Right, you get from one term to the next by multiplying by r. So this is the ratio of consecutive terms. Okay. Where have you seen geometric series before? Repeating decimals. Repeating decimals always lead to a geometric series. Just take, for example, this one. 3.1, then 215 repeating. So it's 3 plus a tenth. And then after this, get into the repeating part, we'll take that much. That's 215 over 10 to the fourth. And then this much is 215 over 10 to the seventh, and so on. So this piece here is a geometric series. Here's the first term, and the ratio is 1 over 10 cubed. So this much converges to the first term over 1 minus the ratio. I don't really care about the number, but the point is it converges. And then you add the first couple terms on, 31 tenths, plus that, and you get an answer. Every repeating decimal can be analyzed like this to turn it into a fraction. This actually shows that it's a rational number. It's the ratio of two integers. I mean, here you have to do the arithmetic and add them up, and you get the ratio of two integers. So that's geometric series. They are by far the easiest because you get this nice expression for the nth partial sum, so it's easy to figure out the limit. You'd be surprised at how often they come around and how useful they are. Well, what about something else? How about a series that diverges? This is probably the most famous one. It's the standard example. It's called the harmonic series. Summation 1 over n. So that's like 1 plus a half plus a third plus a fourth, etc. So here's how we show it's divergent. Amazingly, this method goes back over 600 years. So I'm going to look at the partial sums, not all of them, but the ones corresponding to a power of 2. So the second and the fourth and the eighth and then the 16th and the 32nd and so on. So the second partial sum is 1 plus a half. The fourth is 1, a half, a third, a fourth. But now a third and a fourth, well, they're bigger than a fourth and a fourth, right? Because a third is bigger than a fourth. But this adds up to a half. So this is 1 plus 2 over 2. Now go to S8. So you have this much, and then you get the next four terms, the fifth, sixth, seventh, eighth. But each of these guys is bigger than an eighth. So this is bigger than the previous plus an eighth, an eighth, an eighth, an eighth. There's another half. So I already had 2 halves, now I have 3 halves. So this is 1 plus 3 halves. If you went to the next one, if you went to S16, then you would have all these terms, and then you'd have a 9th, a 10th, an 11th, a 12th, a 13th, a 14th, a 15th, and a 16th. And that would be 8. That would be 8 more terms, each at least a 16th. So you'd get another half, and so on. In general, partial sum corresponding to 2 to the n is bigger than this number. But this number goes to infinity as n goes to infinity. In other words, if you let n be large enough, you can make this partial sum be as big as you want. All right, because if I wanted the partial sum to be over 1 billion, I pick n like 2 billion. Then this would be 2 billion and 1. So if n is 2 billion, then I'm looking at 2 to the 2 billionth, a very large number, but nevertheless a number. And the partial sum corresponding to 2 to the billion would be larger than 1 billion, and so on. So the point is this limit goes to infinity. So that says that the series diverges. So some converge, some diverge. So of course the natural question is, how can we tell which it does? So the first result along those lines is this. If it converges, then the nth term must go to 0. Right? Because you're adding more and more and more terms. So if you want to have any hope of having it converge to some finite number, you need that you're adding smaller and smaller pieces as you go along. As n gets bigger and bigger, this number has to get smaller and smaller and go to 0 in the limit. So now the converse of this statement says if this is not true, then this is not true. If the limit of the nth term is not 0 or does not exist, so either one, then the original series diverges. So that's like a test. It's like a first test. If someone hands you a series, the first thing you do is you say, let me check and see whether the nth term goes to 0. Because if it doesn't, then the thing diverges and we're done. But what if it does? Then it's passed this test. But that's not sufficient. That's not good enough. It still might not converge. It might converge, it might not converge. We need some other tests. So how are we going to get some other tests? Stay tuned. That's what's going to go on in these sections. What I've been talking about right now is the second section of this chapter, which basically introduces the notion of a series, gives you a few elementary examples, and then here we have to start saying, okay, if you just give me some crazy series, what can I do to decide whether it converges? So stay tuned. This is our next order of business. See you then.